You can start. Okay. Okay, hello everybody. Good morning. Hope all of you are doing well and you are fine, staying safe. Do you have any question about last classes and last week course? Okay, good. You may find exercises, homeworks a little bit challenging, but that's very nice practices for you. No worry too much about the marks, just worry about the course itself and learning, because when you're doing that, you're developing your different skills. Problem solving, understanding the course, and programming. That all of these are crucial for your career, for your future. So how much you dedicate time, that's best for your future. No worry about the challenge that you're dealing with. If you're not understanding, you're not successful completely, still that's fine. No worries, do your best. So, and this course, of course, implementation, understanding is one of the hardest ones. So I understand that too, and if you are not completely successful, that's fine. Don't be disappointed. No worries. Okay. Today we are going to talk about a new algorithm, Unscented Kalman filter, that is development of the extended Kalman filter. We will again have some math. In some parts you may find this a little bit challenging, but I will try to break it down as much as possible to make it understandable as much as possible today's course. So what we are going to talk first, we are going to say, okay, what was the challenge in extended Kalman filter and in its linearization, so that we can improve it with another algorithm named Unscented Kalman filter. And in this chapter, we're gonna see how challenge existing in linearization of the extended Kalman filter and how we can improve it by seeing new algorithm and new technique. So if we want to talk about the objectives, we say in Kalman filter, we only was able to use linear models. What does it mean? It means that we only were able to feed Gaussian distribution to our algorithm to be able to solve the problems. So we consider that noise is Gaussian and noise is uniformly distributed. So when the noise is like this, so it means that like your sensor, your model has a noise that is formed in normal distribution. But later we saw that, okay, the noise can be different. The noise cannot be always in Gaussian form. Because of that, we introduced new model that was extended Kalman filter. So that only thing that we did was mathematically converting this guy over here to this guy, then feed it to algorithm. That output again will be this one. So all the efforts that we've done, converting that to this one in extended Kalman filter. Of course, we saw mathematically how we can do that and how we can bring it from nonlinear model to linear model. And we use Taylor expansion. But now we want to see, okay, what are the challenges and how we can improve it with Unscented Kalman filter. The general idea is very simple. You're gonna see soon, but making that simple idea to work is a little bit challenging, especially mathematically. So what was happening if you wanna have a look at Taylor approximation in extended Kalman filter algorithm? So we said that we have this term that we are kind of with G we are trying to linearize nonlinear function. That we mathematically saw how we can first Taylor expansion solve this problem. Anyway, this is like a standard approach that we can just one time implement and always use it. And what was visually happening? Visually was like we had the Gaussian distribution in multivariate or 2-dimension. Here that's 1 dimension, here the same in 2 dimension, the error. Then we have the mean, and we were transferring this Gaussian distribution and mean to another Gaussian distribution and mean that we have a nonlinear function in middle, kind of transforming the distribution to another distribution. So visually, if you want to see, it looks like this in extended Kalman filter. But now we have unscented transform. Unscented transform says, as like UT, says instead of considering only the mean and covariance to do that, we can find some sigma points and use these sigma points to transfer our Gaussian model distribution with some nonlinear function. So we have 2 steps. First step, computing in unscented Kalman filter. First step is computing the sigma points that will give us opportunity to transfer this model to another distribution with function g. That this function g helps us to again solve the nonlinear problem, solve that transformation over there that we have, that one. So Gaussian distribution, we find some sigma points. We will discuss how to find it. Then in second step, we transform each sigma point through nonlinear function g to another form. After we did that, we again need to recompute the Gaussian from transformed points with some weights. It means that we can calculate this distribution based on the points that we have and find also the mean. So whole idea of the unscented Kalman filter is based on these 3 steps, that 2 of them is basically important. G is the nonlinear function that will give us the opportunity to transform our Gaussian distribution to another form. That this G includes our noise and error in a nonlinear form. Any question? Is it clear for everybody so far? So when we are talking about unscented Kalman filter, you quickly should imagine this example, finding sigma points, transform them with function g, and reconstructing the sigma points again. Yeah?
How can we find the sigma points?
We are going to discuss it. We have long history too, lots of math. Then the function g, for function g, we're gonna find some weights. So in order to be able to move it to another distribution. Okay, any other question? So now we want to enter to talk about how transform each sigma point through nonlinear function g. So the main idea is looking like this visually, that we have the mean, we want to find some sigma points and transform. So simplest function that we can have in order to do this is identity matrix. If we have identity matrix, exactly whatever is happening over here will be copied over here, right? Exactly transformed whole Gaussian distribution. So meanwhile we are doing this in order to solve the problem and finding some weights and selecting the sigma points. That this number of sigma points also we can discuss in simplest form. If we have 2D, we can simply find 4. 4 plus, like if you want to consider also the mean itself, 2, 5. But we can have more sigma points in order to bring more accuracy, in order to convert whole distribution to new distribution. So meanwhile, we have some limitations. Limitations will kind of make a platform for us in order to say how to do that. First of all, we say that when we are looking for the weights, the sum of all of the weights should be 1 in form of probability. The weights that we are going to transform these sigma points to another Gaussian distribution. Then second limitation or constraint says that, okay, we need to also, after transforming the first distribution to second one, the mean that we are calculating from weighted sigma points should be the same as the first one. So it means that you cannot transform this from A to B, then the mean is something different. You should maintain same mean with the sigma points that you have. It means that you can distribute your data points, but after transformation it should be at the same. So that we want to find somehow the weights that these sigma points should lead us to the same mean that we have at the first distribution. Okay? And the third constraint says also the covariance should be the same. So you cannot also change the covariance. So because if you change the covariance, you're messing. As much as possible, you should keep the same mean and same covariance after transformation. Because whole idea is linearization of the nonlinear function that we have, and we want to keep everything same. If we have like nonlinear function, then the mean and the covariance, we try to keep it same. So that's the whole idea of after transformation in Gaussian form. Okay, clear? So how we can do that? We can calculate the covariance. Here, just calculation of covariance is simple. The differences of each one of the sigma points with the mean. And that it will come from the weights that we can calculate for each one of those sigma points. So now we should answer how to select each one of the sigma points x's at first step. So you can think how this can be possible. What do you think? What can be the idea? You have a distribution, and this distribution has a mean. We want to choose some sigma points. So the simplest form can be like going to the axis right, going to the left, going to the right, if you want to choose 4 additional ones. Or if we consider the mean itself, it can be considered too. So the idea is this, and we simply want to see how we can mathematically do that now. And after doing that, we need to also answer as step B how to find proper values of each one of the weights that we want to do the transformation. So meanwhile that we are doing that, again, we need to respecting the constraints that we have. You cannot find the weights that are exceeding this, or change the mean, or change the covariance. You should find some proper values for those that we are limited to the constraints that we have. To do that, of course, there is no unique solution, because you can choose hundreds, thousands of different forms of sigma points that can do this, satisfies these limitations, and do the same thing. But there are multiple approaches that today we are going to see what are the most common way to solve the unscented Kalman filter. So now we want to talk about how to choose the sigma points, x's. So first of all, the simplest thing that we can consider is as I mentioned, is the mean. So mean itself is very clear, and this can be as the most important sigma point that we have. So we can consider first x0, sigma point 0, as the mean that already we have in order to do transformation. Then Then in order to find another sigma points that you can see visually here, like these points, we can have a term that this term mathematically can help us to do this. So xi can be equal to the mean that we have, the reference point kind of, added by some value, and if I want to show you the next two to understand it better, and subtract it with some value, so that we can calculate the additional sigma points that we have. But what are these? Now, of course, we're gonna discuss in details. First of all, we should say that the n that we have here, n 1 to n, is the state dimensionality. Then we have lambda, that this lambda is the scaling parameter, how much we want to scale. And also, so we can say kind of distance from mean. And the I is just the column vector that is based on the state dimensionality that we have. So we have some very simple equation that with this simple equation we can find the mean and the other sigma points. And we will discuss also how to adjust the properties. Like n is clear, state dimensionality, you put the value over there. And this is the covariance that is existing over here. We can put it there, and this lambda can be adjustable. But the problem that we have here, the difficulties that we have here, is this square root of matrix, because this covariance is here the form of the matrix, and if we want to get the square root of the matrix, what we have as challenge. What's the problem over there? Square of matrix. Is it easy to solve? Not really, because we don't have one unique solution for square of the matrix. And there are different mathematical approaches to deal with it. Because you can find multiple different answers for form of matrix for multiplication. So that's the challenge, that we need to first also see how to solve this problem, but the rest just some values to replace there and find the sigma points, proper sigma points that we want. So any questions so far? Is it clear? So same thing for the subtraction of the mean with the same equation. And here we say, okay, if we want to consider 2 dimension, 2n per each dimension we can consider, so that in 2D we need 5 sigma points, 1 plus 2 of the sigma points. We can consider more and increase how much more you have. You can increase the accuracy of the transformation. In the end of this slide, we will gonna see visually how it's happening, also that you can understand it better. Now, in order to deal with the square root of matrix, we should have a look at some math a little bit and have a look at linear algebra. So what is happening over there? We have solution for square root of matrix that is kind of changing the square root numbers to matrices, and a matrix that have several square roots and can be calculated by diagonalization. So this is one of the approaches that with diagonalization we can solve it. If we say we have matrix A that is equal to LL, then we can write L is square of the matrix A. So how this can be possible? It is like the linear algebra solutions. We have diagonalization that we can say square root of matrix is equal to, for example here covariance, is equal to L, the matrix L, times the diagonalized matrix of the data that we have in the matrix, that are in diagonal form times the matrix, the inverse of the matrix. Then is kind of this D can be represented is two times of the matrix D that is half of the value of the matrix that we have. So that can be considered as two diagonal matrices that they are timing to each other. So I think I have the example here. Yes, here you can see this d to the power of 1 over 2. That you just need to, in order to solve this problem with linear algebra, you need to deal with this this term over here in order to find the square. And instead of this d over here, we can replace d to the power of 1 over 2 times. And since this is diagonal, and multiplication of those two can that each one can be squared, each one of the data that we have, then can help us to solve the square root of whole matrix here. So of course this is math problem, but this solution has some difficulties because it is not stable for all the scenarios. Because of that, we are going to see the another approach that is more common. So the problem that we have, we say, first of all, real matrices may fail to have a real square root here, and some of the matrices have no square root with this approach that we have. So because of that, that's not stable, and that's the reason that I'm not showing examples, implementations, and all the calculations. But if you are interested in, of course, have a look. It's very simple. You can just even study the Wikipedia to see how that's happening. Just this D will be times 2 this 2, and this is the matrix that you have. You want to get the square root. So in order to deal with this problem with linear algebra, we have Cholesky factorization or decomposition approach that deals with this problem easily. So again, the whole idea is finding sigma points. We are going to calculate the equation that we have here. Those are just simple values that we replace inside. But here we have the matrix, that this matrix, since it is under square, we cannot find easily the solution. We are looking at the mass to see how to solve that problem. So second approach is Cholesky factorization. That says, we say it is another definition of the square root matrix, is numerically more stable, and in unscented Kalman filter, it is very common to use it because it's more stable. So considering again the A equal to LL, and then the L equal to square of the A, what we can do calculate the form that this form that you can see here. So what we do, we need to calculate, first of all find this matrix, second find this matrix, then the multiplication will give us this symmetric matrix that helps us to find the Cholesky factorization approach. So before going in detail how this is happening, I'm going to show you how this is happening. We say that, okay, every real valued symmetric positive definite matrix has unique Cholesky decomposition. So symmetric is clear, I think you all know, but positive definite also, who knows? Okay, I'm going to show you also how we can say if it's positive definite matrix. So consider we have the matrix A in this form, and we want to solve it with the square root. What we do, first of all, we need to bring it to the form of the A equal to LL in two forms, lower triangular matrix and upper triangular matrix, so that if you calculate it, we will have a symmetric matrix looking like this over there. This matrix is kind of mirrored, and the diagonal is the main diagonal is the same, and it is mirrored on the top and down. And if, for example, if you want to like see a numerical example, like is like this for symmetric, like 63696, that if you see, this is the copied over there. How that is happening? Let's move forward. Oh, before that, we need to see some also definitions and limitations. First of all, we, as I mentioned, how we can say we have a matrix that is positive definite. Because if it's not, we cannot use the Cholesky method. But basically, you may ask, okay, if we cannot use it, then what to do with unscented Kalman filter? We design the algorithm at the beginning to don't fall to this scenario simply. But you need to know how positive definite definition is looking like. We say if the matrix A with multiplication of the vector V as follows is positive for all real numbers except 0, it looks like that. So we have a vector V times the matrix that we have, A, times the vector V is greater than 0, where we have the V as real numbers, all possible ones that you can find out what to place there, and the V is not equal to 0. So it looks like this. If you, for example, if we want to check the identity matrix and replace it as matrix A over here, then per all the values of the V1 to the power of 2 added by V2 to the power of 2 is greater than 0. And this is always positive. Because this is always positive, we say it is definite, the positive definite matrix. For example, identity matrix is positive definite. So you can now consider this to say that the matrix is positive definite, but how we can do it in Python? Is it complex? No, already well-known problem in math, and you just need import NumPy, and with NumPy, just you need to find the eigenvalues to tell that if it's positive definite or not. So if all the eigenvalues of the linear that is coming from linear algebra of the matrix A are positive, we can say that it is positive definite. So who knows what's the eigenvalues? Okay, you don't know anything about algebra and math, I guess. So that's what we need all here in the. Okay, what is it? You just only how to solve, you don't know what does it mean. That's not useless. Oh, we have a slide, but for that I will define it in details. But I can say, like, if I want to simply show it on distribution, so this is Gaussian distribution. So the relation between these eigenvectors, we call them as eigenvectors, the ratio of the change between these two, how much they are like, it is like this or it is like that. The ratio of the what are the differences between the scale of the for example one distribution. So this is used over there. Then this ratio can help us describe the distribution basically here, right? Because okay, before this, we were talking about the mean and covariance, right? But the covariance here and here is different, right? Eigenvalues can help us to describe that too. What is this one and what is that one? Because covariance in one dimension is okay, but in two multivariate, then not anymore. That's why we need the eigenvalues. As you can see here, you can like import a matrix, create a matrix, then calculate the eigenvalues. NumPy dot linear algebra dot eigenvalues of the matrix A will give you the eigenvalues that I showed you over there. Yeah, here, I thought I have it a couple of slides later. So I define that when a linear operator is applied to a vector, the vector's line of action is unchanged, first of all, because of the definition. So when we are linearly changing this to some other form of distribution, so we should maintain this ratio, right? If we change it, then that's totally different thing. The distribution is changed. We should maintain the ratio. Maybe it can be bigger, but the ratio should be constant. So that's what does this mean? Then we have the we say, okay, eigenvalues used to identify features of large data sets and performing dimensionality reduction, because like if we say this is data set and there are millions of points over there, instead we can say, okay, ratio of the data, the relation between data on the x and y. Then with two values, you can reduce the dimensionality of the data that you have a lot dramatically with the calculations of the eigenvalues. And as I draw there, you can see that we have some definitions, eigenvectors, the main diagonals, vectors, these two are eigenvectors. And each eigenvector has eigenvalue. For each one of these, we have eigenvalue, and the ratio between those are the most important thing that is between two these, and I explained for you already. Any question? Clear? Okay. Now let's go back here to the discussion that we've had. Let's see how this is happening. Simply, in order to understand this, the square Cholesky factorization or decomposition approach here that we are calculating this matrix, how that's happening. If you have a look, simply to calculate this column over there, you can say, okay, the calculation of the, so we want to find the square root of the A, right? And we want to find out this calculation based on this term over there. Then we can say the AA is equal to L112 to the power of 2, this guy over here. That we can actually rewrite it in the form of L11 is equal to a square of the A11. So we calculated the square, the square root of the A11. Is it clear? So again, look at here, A11 is equal to this term over here, okay? This guy over here. So that we are actually calculating the L11's the square root. That A11 is square root of the A11. So, and if we continue that, like for the second term over here, A21 from this matrix is equal to L21 times L11. L21 times L11 over here. That we can write it, L21 is equal to A21 over the L11 to calculate the square root of matrix that comes in this form for the whole symmetric matrix that we have. For A31, we have L11 times to the L31. So we can show you that. So for L31, this one times this one. That comes from there also. And now if we continue, like for second column, you can see that for calculating A22 on the main diagonal, we have the calculation of this term over here, like this, comes to there directly because we are on the main diagonal. That we can rewrite it as L22 is the square root of the A22 minus subtracted by the L to the power of 2 of the 11. And we can continue that for the A32 to calculate the third one over here. So this is like kind of the matrix calculation that represents how Cholesky approach is mathematically finding the calculation of the matrix that we have over here for square root. So it is clear, just matrix calculations. If you just look at the matrix multiplication of the symmetric calculation over here, then replace it, you will see that simply we are achieving that. And if you continue even for the third one, you can see that A33, that is like again on the same column, will be this guy over here, this guy over here. A33 is this one, then that's it. No need to simplification. And lastly, as one example, that actually L33 can be written as, since these are to the power of 2, we can write them all in form of the square. So, but how we can? Okay, let's say you completely understand. This is simple math of the matrix calculation. How to implement it in the computer and in the program code that we have. I did it for you guys to make it clear. So we need two for loops indeed that we can find out, extract first of all the pattern of calculation based on what we see here. Based on what we see here, we can find out the form that we need to have two nested loops. First of all, like I from j, and for when I is not equal to j, we can calculate this term over here and this term over here. That the calculation of the L of the ij is square root of the ij subtracted by sum of the k equal to 1 to j minus 1 and sum of the each one of those. So what this is representing? This is representing the calculation, all the calculation that we have here, just with the pattern form. Then for the cases that I is not equal to j, we do this one. So here the I is the inner loop for rows, and here j is the outer loop for columns calculations. So if you run this simply, you see that we have previous example implementations exactly. This is just pattern of how we did that. It's like simply matrix multiplication that does the calculations in form of the algorithmic presentation. Then even we can I also stated for you that this is for main diagonal update. Basically, calculation of main diagonal is in charge, and this is the under the main diagonal update. So I've placed the example implementation here, both in two languages. That the implementation of these for loops, you can see the for loop j equal to in range of n, and I equal to in range of j and n, and it's like if the I is equal to j, the term that we have here can be placed here. Otherwise, the other term we have there over here, simply. So what is this implementation doing? Exactly, implementation of the Cholesky approach in order to solve that square problem. Now that square problem can go back to the term that we have, the term to find the sigma points. Clear? So this Cholesky, let me see if I have it next slides. Not here, but let me go quickly back here to make it very clear for you guys. So all efforts comes to here. Comes to solve this square root matrix problem here. Cholesky method deals with it. Clear? Any question? So of course, today I also will give you some time after finishing the topic to have a look at the implementation and see, double check and run it to see what's happening and maybe calculating to make it 100% understandable for yourself. Now, we need to move to second step. What is the second step? How to find proper values per each one of the weights that we want to find. So let's say that equation already solved. We found the sigma points. Now we want to, those sigma points, transform them to the new distribution. How that is working? There is the term that is doing this for us. So for case of the W0, the weights for the 0, that is the weights for mean, can be written by this term. Lambda over lambda added by n. That is, again, the scale sigma point spread, how much we want to spread. And this term helps us to find the W0, weights of 0 of the mean. So you just give the scale, you give the dimensionality, and this gives you the weights that you want, how much to spread. On the other hand, when we want to find the covariance of the same, consider the weight 0 based on the covariance that we have, we can consider this term over here, that the W0 and covariance that already we had is added by this term over here, one subtracted by square of the alpha added by beta. So what are these values? These values already are calculated by mathematical guys. If you want to do the find the values, proper values for these guys, you need to familiar with exactly the specific problem and the distribution that you have, maybe based on different distributions that can be vary. But already this is solved in Unscented Kalman filter. Even if you have a look at the book, it's already proposed the values, best values for this, and everybody just simply use it. Don't need to reprove and go all in the math. But you need to generally know how that is happening. But so I will show you in these slides. What about the rest of the things? This is for W0 and W0 mean and covariance. That is for mean, for the mean, this point over here as sigma point. For all other sigma points, we can, for both of the mean and covariance, it will be same. We can use this term over here. 1 over 2 times of lambda added by n, that is, n is the state dimensionality. Again, this is the how much spread that we want to have, and simply we can calculate it. So the values I've showed to you that alpha is between 0 and 1 usually, and you can like change it to see the accuracy that I will show you the results after the implementation of the whole Cholesky method. And the optimal value for Gaussian distribution that we have is 2 over here. So Y2, they already tried it different values, and they found out that 2 is the best value over there, simply. Not a specific reason. You can change it even based on the distribution that you have. You may have, like in future, very big complex problem. You want to say, okay, now I know that this beta over here can be changed. I want to change it to increase the accuracy that I want in Unscented Kalman filter. Okay. So I also explained that you need to have extra information of the problem, and increasing of the alpha and lambda increases the just spread. How you increase the value between 0 and 1, you spread it more and spread it less. This is like general rule that we have over there. So how does it look like? I presented here that also in interactive book you can see the implementation of what we explained, exactly the same terms and same implementations. If you, for example, put the alpha as 0.3, you will find these points, sigma points, and here alpha is equal to 1. You can see that the spread is much more spread for the transformation approaches, the transformation that we want to have. But now, lastly, what we need to do, as I told you, we need to, after finding sigma points and transforming them, and if we want to write the transformation in form of this is like I'm mixing. Transformation is like if you write it as g, the function g. So we need to reconstruct the distribution that we have, the Gaussian distribution. If you want to reconstruct it, what we need to do, simply finding the mean the new mean, the mean here, is the sum of the weighted, the sigma points that we have. So we found some sigma points already. This G is nonlinear function that we gonna, the noise, the model that we have, we're gonna apply. And the weights that we have found, then we just find the sum of all of them, then we can find the new mean. What about the covariance? The covariance calculation is the same that we showed at the beginning, but here we have G instead. And this G that applies on the sigma points will give us the new covariance, like we can call it the covariance prime and mean prime as new calculations. So to make it more understandable, let's move a little bit to here. This figure will clarify everything what we will study. Look at this guy over there. So we have a nonlinear function. We have a nonlinear function that looks like this. This is a distribution that is not Gaussian. And you can consider like this is the noise of the sensor model that we have or something. This is the mean over here. And this is the distribution itself. So what is happening? Now we want to have the function fx in order to transform it to Gaussian distribution. How that's happening? Like per each one of these points over here, if you match it, like draw a line from there to down here, and for each one of these draw a line from there over here, that for example for mean you can see this red one that comes from there to here, and plot it to this one, like after applying whole of that over this guy, and the things that is distribution, you will have like this. So you see that this nonlinear model converted to linear model by just each one of the points. You draw a line, match it, and match it on the distribution. What is happening visually looks like this guy over here. Is it clear? This is very important figure to understand. Just you can imagine like this guy, you plot, and over here, because this is like these points over here a lot, and comes to form out the Gaussian distribution. Then let's have a look at the let's have a look at the real example of the and comparison of the what is happening with extended Kalman filter, unscented Kalman filter. So and have a comparison over there. Like now, if you want to see and discuss that, okay, this model that we have, this distribution that we have here, we apply this function Jx that is nonlinear function, and we do the same based on this distribution that we have, applying nonlinearity function to kind of revert it to see what is happening. We are actually kind of reverting what's happening, but there we are trying to do this to give it to the algorithm to work. To make it revert to what's happening, if you look at the extended Kalman filter, we have the Gaussian and extended Kalman filter Gaussian comparison here. So this is what the red one is what extended Kalman filter Taylor expansion calculation is doing for us. You can see. And this is the blue one is Gaussian of the function that we have, and this is like the model of the noise that really is existing. We applied a Taylor expansion to make it Gaussian. So this is really what is happening in the environment, the noisy environment. With applying Taylor expansion, whatever is happened with extended Kalman filter, we achieve this red one. Okay, we solved that problem in order to be able to deal with the problem, the red one. And the blue one is the what is really it is, what should be supposed to be really. In extended Kalman filter, you see the error, but with unscented Kalman filter, the red one is more close to blue one. More accurate. Why more accurate? Because Taylor expansion is only using, relying on the old calculation is relying on the mean and covariance. It means that it was taking into consideration of the mean and covariance only. But here, we are kind of giving more sigma points in order to help it with unscented Kalman filter. And these sigma points give us more accuracy so that you can see the noisy model, the noise, that really if it's considering this is the blue portion, the real Gaussian of the PY, the unscented Kalman filter is more accurate. And how this is happening, again here, for each one of the points, just put it there and plot it here. Like this is like one example. If you put a point here, comes here, and plot here. So if you do for each one of those, you will achieve that red ones for unscented Kalman filter, especially because the other one comes directly from Taylor expansion, mathematical calculations. Any question? Is it clear? So the most important one is the motivation of the and general concept of the unscented Kalman filter. If you understand it, the rest is implementation. Now let's have a look at the algorithm. I'm not going to explain all details because that will be, we want to just compare with extended Kalman filter, see what is happening and what we adding inside. Because we already also have seen, and that should not be very complex to understand. But generally what we are doing, we are trying to do this slide over here and to see how this is happening and all the calculations. So we had the already extended Kalman filter, just load it up in your mind again. We had the function g as Taylor expansion that we used some matrices. We used some Jacobian matrix in order to find the mean and covariance as prediction step. Then we applied the correction step and returned the new mean and covariance. That was the whole idea with unscented Kalman filter. So the most important thing was mean and covariance that we have. Now, if we have a look at the unscented Kalman filter, of course, it's again bigger and more complex. Looks like you can see from line 1 that we continue to line 12. Whole motivation again is that the previous mean, previous covariance, and observation comes to the algorithm, and finally new mean and new covariance will be returned. The whole idea. But let's have a look in details what is happening. Generally, we have these 3 lines at prediction step that works based on the observation, but now we know that we need to find sigma points. The same equation. xt's and same term that we've seen. We saw that, for example, to solving this, we need Cholesky approach. Then we calculate the mean. Based on that, the calculation of mean is weighted. The function g, that is nonlinear function that is like does the plotting, and applying this nonlinear function on the xt minus 1s, the sigma points that we have. So visually, here, we have the Gaussian distribution. We find the sigma points, x's. We apply the g, and we find the new one. And g is this guy over here. Then after finding the predicted mean, we find the predicted covariance, the same finding the covariance approach. Just here we add again the G plus the weighted G's that we have. Finding the covariance is the differences between the mean and how it is distributed over there simply, and the weighted one of those, and finally adding some noise. And this noise is observation noise that we have, same as extended Kalman filter. So we already broke down this, studied in these slides. Broke down these slides and it's broke down in this slide study. Just we have the G here as kind of a little bit new. I made it as blue for you. Then we have the correction step. In the correction step, what is happening? Let's see. In line 4 to 6 here, you can see that we have the we calculate the predicted transformed x's based on the transformation that we have. And here we have transformed sigma points through function h, because we have two, one for control commands, one for observation in correction step, and odometry, that first calculation. So since we are in second step here, the function of course will be different. There was G, here is H. One for observation, one for example, motion model. So for correction step, then again we calculate the in the correction step the predicted observation from sigma point based on the vision that we have. Then it goes to calculating the Kalman gain. And for the calculating the Kalman gain, we have a couple of steps. First of all, we calculate the some points ST, and based on that predicted covariance and calculations of the Kalman gain. And based on that Kalman gain, we're gonna see again how much motion model, how much observation model should be applied on it. So I put it some points over here. For example, uncertainty QT, again another uncertainty for observation model we have. RT was for motion model. QT is the error that we have in the observation model, exactly same as extended Kalman filter. And what we have here, using sigma points propagation to Kalman gain calculation, in fact process of replacing H in UKF. So there we were like using Taylor expansion and calculations of the H in order to find the Kalman gain. Here we do this one, finding the weighted the covariance of the sum of the weighted covariance, like this is the covariance calculation that over here, in order to say the Kalman gain based on these sigma points and covariance, how much should be applied on the observation or control command. If you have a look, pretty similar. Kalman gain, so the predicted mean that comes from motion model here added by the observation. Kalman gain says how much observation should be affected. And observation is the differences between observation T and predicted observation that makes the differences. So the same, the whole scenario and whole idea is same, just the calculations becomes based on the unscented Kalman filter. Then what we have here, we have the update of the new mean and new covariance. Finally, after the calculation and Kalman gain, the Kalman gain helps us to calculate the new mean, new covariance, and return them. So for here, I've written that output of the sigma point from observation function, that Kalman gain does that, and pretty similar that what we've had in extended Kalman filter. If you remember, in extended Kalman filter, the term were looking like this. Here, we just have that one instead. That's it. So now let's compare them. If we run these different techniques, what they are looking like. This is coming from your book, I think, or a paper. I think I bring it from a paper. I don't remember exactly, but anyway, this is the source. So if we use the extended Kalman filter, So this is the distribution that we have, and this is the mean. And we apply the Taylor expansion, if you remember, first Taylor expansion algorithm. Then this distribution, this is the what we have. The new mean and new covariance. That is kind of, you see that in extended Kalman filter, although we said that's good algorithm, that's nice, but it has error, and that this is the error. Then what if we apply the unscented Kalman filter? So we find the sigma point based on this distribution, and we apply the function fx, that is nonlinear function on it, and you can see this green one, that is unscented transformation result, that is much more close to the distribution, the first Gaussian distribution that we found. Why this is happening? Because here just mean and covariance has been used, but here these points are helping us to do the transformation through that nonlinear noise that we have. So what do you think if you want to get 100 accuracy of the transformation? How we can achieve it? So let's say if I ask you transform this Gaussian distribution from nonlinear function and get 100 very accurate, very high accuracy. Although this is accurate, but there are some errors too. How you can achieve very high accuracy? Yeah? Yeah, we can use infinite number of points to generate it, and that's what you see over there. You can generate millions of points, transform them, and it will be exactly overlapped on it. That's called sampling. Also, we will have some techniques that is based on sampling. For example, particle filter. We will study and see how particle filter works based on the sampling, and how can help us in these scenarios. So we kind of seeing algorithms to improve it, but sometimes after improving, I will tell you that that improvement also has lots of problems also. Because of that, you need to choose which one you are using. Although we are improving, but you may study recent papers that they are still using extended Kalman filter and propose very nice technique, or unscented Kalman filter, very strong approach. So that's why we are studying this. Otherwise, you may say, okay, come to the end one and study directly that one. We don't need to know this. There are two reasons. First of all, impossible to understand that last one. You have to come from scratch to see what's happening. Second reason is that we are not concretely can say this is the solution for everything. So because you should be able to develop and understand different techniques, and based on what you are doing, to choose and apply on the problem that you have. So what about the implementations? What about the examples that we can have? Of course, you can have a look at the interactive book. Again, there is like pretty nice example that how you can implement interactively. And on the other hand, you can refer to the Python robotics. I think, let me see if the link is working. Hence, that is better to follow. So for today, as exercise, you need to do generating 10 random multivariate two-dimensional Gaussian distribution randomly, generate 10 of those, and that they have random mean and covariance. Then generate 11 sigma points per each one of those and plot them. So just first step of the what we studied today, generating of the sigma points on each one of them. Of course, part of it also has been shown in the book. You can have a look, but you need to do it today as exercise. And if you want to have a summary of today's course, we discussed the extended Kalman filter challenge. Then we discussed unscented transformation, how it works, how unscented transform works better than Taylor expansion, and how UKF uses unscented transformation. So now you can start to work on this assignment and see what is happening in details. Any question? Okay, good.